Well, hello and welcome. In this video, I'll be covering the section 1.2, which is just over graphs of equations. So my goal for you by the end of the video is to be able to sketch graphs of equations by hand, to be able to find x and y intercepts of graphs, to be able to write the standard forms of equations of circles, as well as the general form, and to be able to find points of intersection between two graphs. So let's start with just how to best sketch a graph. So one of the more basic ways to do this is to just create a t-chart and plot points. The downfall of this is if you don't plot enough points, when you connect them, it may not give the correct shape of that particular function. So this does rely a little bit on knowing or expecting what shapes you're going to actually have once you plot points. So you can do this in form of like a t-chart, or you can even do like a horizontal table if you didn't want to take up as much space. But essentially the concept is you're either going to select x values or y values, depending on what looks like it's easier to plug into, and then solve for whatever the remaining variable is, and then that collection of those values would turn into a bunch of points, where again you would plot your x, y for each one of them, then connect with a smooth curve. So with this example, if I just kind of demonstrated a t-chart, for this one it looks like I have an input value of x, so I probably want to choose x values. Some numbers that seem reasonable to try would be like -1, 0, 1, and 2. That might be more than I really need to be able to do this, but if I plug these values in, I would just put the -1 where that x is, so I'd have 4 minus 2 times -1, which would turn into 4 plus 2, so 6. Then I do the next point, plug in 0 everywhere I see x, so 4 minus 2 times 0, that would just stay 4. Then plug in 1, 4 minus 2 times 1 would be 2. And plug in 2, 4 minus 2 times 2 would be 0. At this point now I would just go over to my grid and actually start plotting some points. So if I go to the first one, it would be -1, 6, which is a little too big for the grid. 0, 4, 1, 2, and 2, 0. Looks like to me there's no curvature that's happening, so I should be able to go ahead and just connect the dots, in this case creating a line, which just by looking at this equation we probably knew that was an equation of a line. Could have also plotted this where I just went with what my y-intercept was and what my slope was. So that example kind of leads me towards this other idea of how we could sketch graphs. We can also use, if we remember common shapes of some certain graphs, such as some of these that are up here, more than likely the exponential, it's been a little while since you've seen that, as well as the logarithmic. And as we encounter those later in this year, I'll go ahead and review some of the properties of those too, but everything else, the linear, quadratic, cubic, absolute value, square root, reciprocal, the other main ones that we have here, what is that, 6 other ones, we should be able to remember kind of what their basic shape is, as well as some of their key points. And we can always try then graphing using transformations, which remember that would involve like if you saw addition or subtraction inside or outside of the function, multiplication or division inside or outside the function, or you even saw negatives, that would do your shifting, stretching, and reflecting correspondingly. So if we maybe try an example of maybe plotting points using transformations, as we can see with this example, we have a function that looks like it's quadratic. I see a power of 2, so I'm expecting this to have generically a U-shape. And what's happening is I have subtraction by 2 inside the function, so that's going to move it to the right 2 places. And then I have subtraction by 4 outside of the function, so that's going to move it down 4 places. And so now if I just take those key points that we hopefully can remember from our graph, normally that U-shape should start at the origin, so if I plot that point first, I would just go 2 to the right, 4 down, plot the point. The next one it would go through normally would be 1, 1, so if I take that same point, go 2 to the right and 4 down, it gives me that point. Another easy one would be -1, 1, go 2 to the right and then down 4. And just keep repeating that process with all the points that we remember. You can also, with parabolas, maybe remember you go up 1 over 1, then the next one would be up 3 over 1 each direction. And there is some symmetry, so every point you plot you can then utilize that line of symmetry, which in this case would be this line x equals 2. And then after I go up 1 over 1, up 3 over 1, the next one would technically be up 5 over 1 if you, again, remember that pattern. But I probably had enough points to be able to draw this U shape without needing those last two that I did. But it ends up giving us a decent sketch of this graph. It's not 100% perfect, but it gets all the points, or at least some of the key points, in the right spots. And then everything from there is just trying to connect them with a nice smooth curve. Now another thing that can be helpful when it comes to sketching graphs would be to actually find the intercepts, both the x and the y. So essentially any point that is a place of intersection with either the x or the y-axis, we just call those collectively the intercepts of that graph. To find an x-intercept in general, all I need to do is just let y equal 0 and then solve for the x variable that's left. Sometimes that might involve factoring. Sometimes you may have to do some other tricks, but essentially still just trying to solve for x is your key idea with that. If you need to find a y-intercept, you basically let all of the x's equal 0, and then you solve the remaining equation for y, which more times than not, you end up only having one y-intercept, but it's not always necessarily something that you're graphing having the requirement of needing to be a function. So it is possible to actually have multiple x-intercepts and y-intercepts, or there's even some situations where it doesn't cross either axis at all. So let's try out a few examples of actually finding intercepts for a graph. I'll start this first one, letter A, with just finding the x-intercepts of it. So that would be to plug in 0 for y. So it's basically going to be solve this expression now that I've created, or this equation that I've created. Looks like with this one being a quadratic, it would make sense to try factoring. So I would need to look at what multiplies to this -3 that will add to the middle term -2. So in this case, that seems like it would be a -3 and a +1. So my x-intercepts for this one, if I were to write them as ordered pairs, if I set each of those equal to 0, I get 3, and we said that the y would be 0. And then if I set the second parenthesis equal to 0, I'd get -1, and again the y is 0. So there's my two x-intercepts. To find the y-intercept, in this case there's only one of them, but if there were more than one, I would go ahead and solve it. I essentially just plug in 0 for all of the x's, so that would be 0 squared minus 2 times 0 minus 3, which that one's pretty easy to simplify because 0 minus 3 would just be -3. So my y-intercept for this one as an ordered pair would be 0 for x and then -3 for y. Let's try one that's maybe not necessarily in this function format. With this one again, if I wanted to find the x-intercept to start, I plug in 0 for y. So that would be 0 squared minus 4 equaling x. 0 squared is 0 minus 4, that would be -4. So my x-intercept for this one would just be -4 comma, and then y is 0, so 0. To find my y-intercepts, similar step, but this time I let all of the x values equal 0, so I'd have y squared minus 4 is equal to 0. Probably want to add the 4 to start getting the y isolated, so I get y squared equals 4. And then with this one I would want to take the square root to cancel that power of 2, but since I introduced it, I know that there should be a plus or minus symbol, and the square root of 4 is 2, so my two y-intercepts for this one would be 0 comma positive 2, as well as 0 comma -2. So this particular one, if I were to graph it, I would expect to not be a function because I got two different y values for the same x value. So this is definitely not an example of a function. So let's move on to the next topic, which was over circles. So just to review, a circle, if you recall, is just a collection of all the points that are all the exact same distance that which we call a radius away from a fixed point, which we call the center. Now the standard form of an equation of a circle is essentially the point x comma y will lie on a circle with a radius of r and center h comma k if and only if it satisfies this expression of x minus h quantity squared plus y minus k quantity squared equaling r squared. Now if I were to want to get that into what's called the general form, all I would have to do is just expand out all of the parentheses that I have and then move this r squared that's on the right side over to the other side, or basically just get it to where it's set equal to 0. So what's the key difference between standard and general? Well, standard you'll more than likely see parentheses, and general you more than likely should not, or in fact you never should see parentheses with a general form. It is important to note that the coefficient a, which is in front of your two squared terms, cannot equal 0, because if it did equal 0, then I would essentially just have a line. So an equation for a circle, there always does have to be both an x quantity squared term as well as a y quantity squared term. So let's try an example. With this one, it says that this point 1, 5 lies on the circle whose center is at -2, 1. So if I know that that's -2, 1 being the center, I could then commit to the fact that that must be my h and my k. Seems like the only thing I'm really missing is what is the r. So to come up with the r, it should just be the distance from that point that is the center out to the point that's actually on the circle itself. So I will have to use the distance formula to be able to come up with that. So with this one, it would be the difference in my two x values, so -2 minus 1, quantity squared, added with the two y values subtracted, 1 minus 5, quantity squared, which in this case would be -3 squared, which is 9, and -4 squared, which is 16. And if I add those two together, I get 25, and the square root of 25 is 5. So now for part A, where it just wants the standard form, I'll do first the x minus the h value, which minus a -2 should actually switch to addition, quantity squared, then added with the y minus the k value, which was 1 from the problem, and it would equal the radius squared, so 5 squared, which is in fact 25. So that radius, we always do want to apply the power to the number and actually just make it look like a number without a power on it. Second part of this, it wants us to actually figure out what does this look like in general form. So I would essentially expand out each of those parentheses. So if I go ahead and start doing the work for that, the first one, if I expand that out, that should turn into an x squared. My middle terms of 2x and 2x should add together to give me a 4x, and a 2 times 2 would give me 4 at the end. Do the same thing with the y parentheses, so that would start with y squared. I'd have a -y and another -y to combine to give me -2y, and then a -1 times a -1 would give me a +1. I'm going to go ahead and subtract that 25 over because I want to get 0 on the other side, so I'm just writing it as its opposite on the left, and now it just turns into a combine like terms and rearrange. So normally we start with the highest powers, so I have x squared. Next one is a y squared. Go with my x term next. It looks like there's only one of those, 4x. Go with my y term after that, -2y, because there's only one of those. And then I've got a 4 plus a 1, so 4 plus a 1 minus a 25, so 4 plus 1 would be 5. Take away 25, that would really take me down to -20, so -20. So again, I have my standard form right here, where the parentheses are there, and I have my general form right here, where notice there's no parentheses at all. We did have to do a little bit of rearranging, but essentially the main concept was expand the powers, move everything to one side, and combine all of your like terms. Alright, so now let's move on to another example where now I actually have to sketch a graph of the circle, and it is actually already presented in general form. So in general form, it's not as easy to identify what my actual center is. So what we'll want to do is to take this general equation and actually start trying to get it into that standard form. So what I like to do personally is get the x's near each other first. So it'd be the x squared and the -4x. And then I leave a little space because this process of making something that doesn't have parentheses turn into something that does have parentheses will involve the concept that hopefully you guys remember was called completing the square. If I move on to now the y's, I have y squared and a +2y. And I'm just going to take that -1 and move it over to the other side because I'm eventually wanting the other side to turn into just a number so I could identify what my radius was. So now it just turns into completing the square. So if you recall, completing the square was to take the middle coefficient, first double check that it equals 1 on the leading coefficient. But I take the coefficient of my x term and I go ahead and cut it in half, which would be -2, and then square it and add it to both sides of my equation to balance. That then should allow me to have this first one in factored form be x minus 2 quantity squared, because if I need to multiply to 4 but add to -4, that would have to be a pair of -2's. And if we do the same thing with our y term, we have our middle coefficient is 2, so cut that in half, I get 1, and square it, which stays 1, and then add that again to both sides to make sure I balance. That then should allow me to say that my y's can now factor into a y plus 1 quantity squared, because what multiplies to 1 that adds to the 2, that should be a pair of positive 1's. Now the other side of the equal sign, I'll just add those three numbers that I have now together. -1 plus 1 is 0, plus 4 more is 4. So once it's in this form, I should be able to identify where my center for the circle is, as well as what my radius is. So my center should be these two numbers, the h and the k. It is supposed to be subtraction, so that's going to be an h value of +2. But since that's a +1 in the other one, I need to think of that like it's a -1, because minus a negative would have been what needed, or what was needed, to make that switch to addition happen inside. The radius should just always be the square root of whatever the number is on the other side, and the square root of 4 gives me 2. So at this point I should be able to now start plotting some points over on my grid over here. So I'd go to 2, -1, plot that as my center, and then utilize the radius, which is 2, and just count each direction out 2 places. So go horizontally left and right 2, and vertically up and down 2, and then we just do our best to connect those with a nice circle. It doesn't have to be precise. Ultimately, when it comes to grading, just be looking to see, did you plot the 4 points, the correct radius out from wherever the center was. And now on to the last concept I want to cover in this video, which deals with points of intersection. So generically speaking, a point of intersection for two graphs is essentially an ordered pair that happens to be a solution point for both graphs. You can also just think of this graphically as it's the place where a graph meets another graph, or they cross over each other. So to be able to find points of intersection, essentially we just want to isolate something that's identical within both equations, and then use substitution to then replace that particular term, and then solve for the variable that you have left. Now, as far as some applications for where points of intersection may become useful, some things that your book will have you doing this year that deal with a little bit more of a business, concept, are the idea of a break-even analysis or finding an equilibrium point. So a break-even point is essentially something where your revenue and cost are the same or equal to each other. So if I had a revenue equation and a cost equation, I would essentially just set them equal to each other and solve for the variable that's left. Or an equilibrium point would be essentially something where like supply meets demand. So that's a concept that maybe you guys, if you've taken an economics class, have encountered in the past. But as far as just the idea of practicing finding points of intersection, let's go ahead and just try these two examples that we have right here. So this first one, if we look at letter A, we've got two linear equations because there's no powers. So I've got x plus y equaling 7 and 3x minus 2y equaling 11. So I have two expressions to try and find something in common between the two. It seems to me like I could make either x or y be by itself, then I could plug it into the other expression. So if I look at my two options in this 3x minus 2y, I feel like plugging in for the x might be a little easier than plugging in for the y, because y has that -2 as a coefficient. So I'm going to go ahead and choose to isolate x with this first expression just by subtracting y over, which then gives me x is equivalent to 7 minus y. Now what I get to do with that expression I just created is now replace the x in the other equation and go ahead and try solving. So if I go ahead and do that, that'd give me 3 times the 7 minus y that I just solved for, then minus 2y being equal to 11. So if I distribute through that 3, that gives me now 21, take away 3y, take away 2y, equaling 11. Looks like there are some like terms, so I can start moving things around. Subtract 21, so I can combine with the 11. And then the negative 3y and negative 2y, that should be able to turn into negative 5y, which equals now negative 10. So one step away to get y by itself, just divide by the negative 5. And I get that the y-coordinate of my point of intersection is going to equal 2. So to get my x-coordinate, what I'm going to end up doing is just utilizing that x equation I created at the very beginning and just substitute that value in. So it would be 7 take away 2, which would give me 5. So in the end, now I can say this did have a point of intersection. The two graphs do have a solution that they share, and it happens to be this point or ordered pair, 5, 2. Now if we try one that's maybe a little bit more intense because it's not two linear equations, let's look at letter B. Notice I've got something that looks like it's probably parabolic because there's a power of 2 and only one of them. And then the second equation looks like it must be linear because there are no powers. So if we think about our options, a line could go through a parabola either 2 times, it might meet only 1 time, or it's possible they don't meet at all. So it is something with this where I go in with an open mind that at most I can get 2 solutions, or I can potentially get no solutions at all. So don't force anything if you don't have to. So if we look at the 2 equations that I got, looks like they do share this y, so choosing one of the 2 expressions to just get y by itself, I think I'll choose the second one, and just subtract 2x over. That gives me then that y would be equal to 1 minus 2x. That now I can take that expression and replace the y in the others. So if I do that, I've got x squared plus this grouping 1 minus 2x being equal to 4. Looks to me like I should be able to kind of rearrange some things, and it does appear as though this is going to be a quadratic that I'll want to probably try factoring. So I'm going to go ahead and just subtract the 4 over so I can get the equals 0 on the right side, because usually that's better to deal with when you have quadratics. And if I get rid of these parentheses, there's just like an imaginary 1 right there. If I distribute that through, those parentheses really weren't necessary. So I do have an x squared term. Looks like I have a negative 2x, and then I've got a positive 1 with a negative 4 when I move that 4 over, which would really give me a negative 3. So now I try the factoring step that I was expecting to have to do with a quadratic. If I couldn't factor, then I might approach this with like completing the square, or maybe just using the quadratic formula. But with this one, there is something that multiplies to negative 3 that adds to a negative 2. I feel like we actually saw that one not too long ago. X minus 3 and x plus 1. And so now I should be able to say that my 2 x coordinates that I would have are going to be a positive 3 and a negative 1. So now I just need to plug that into this y expression from the beginning to get what the corresponding y values would be for each one of those. So at x equals 3, I'd end up with y equaling 1 minus 2 times 3, which would be like 1 minus 6, so that would be negative 5. And then at x equals negative 1, I should be able to do y equals 1 minus 2 times negative 1, which really would turn that into 1 plus 2, which would give me 3. So my points of intersection for these 2 expressions, there's actually 2 of them. One of them happens to be at 3 comma negative 5. The other one happens to be at negative 1 comma 3. So I could, if it needed to be graphed at this point, or if I needed to graph this at the beginning, I would expect those points to be things I could use for both equations. And then it would just turn into making sure that I'm connecting the rest of the dots in a way that makes sense. So anyway, hopefully this video has been helpful in getting you to understand the concepts that we wanted. But as always, if you have questions, just let me know and I'll do what I can to try and answer them as quick as possible. I appreciate you taking the time to watch this video, and until next time.